Hi, I'm Daniel. I'm going to be talking today about machine-assisted validation of drill hole logging data. So I'm from the Centre for Exploration Targeting at UWA. This is some work that we've done with some friends at Rio Tinto Iron Ore. Okay, mouse doesn't do anything.
Oh,
It's the other mouse, is it?
It's the red one. Yeah.
Oh, okay.
Yeah.
It's really hard.
Really hard.
Oh, that's strange. What's going on?
I've managed to do something to the door and yeah, broken the mouse now, so now I've got a menu.
Click off to the side.
Oh yeah, so that goes there. Cool, okay, I can use the mouse.
Okay.
This is talking about some logging data, and Rio gets a lot of logging data from RC drill holes. They routinely log these holes at the rig in 2 metre intervals as a composition of material types. So every 2 metres, the chips come out from the hole. They get split into 2 samples. One of the samples, they get the chips and they log them, for example, as shown up here. So we might have, say, the interval might have been 20% BIF, which is an unenriched BIF, 50% GOE, so each material type is a 3-letter code. So GOE is a moderate hardness goethite. GOL, so it might be 20% in this case, is a different type of goethite, so it's a bit more friable, and 10% shale. So together from this we can, each material type has theoretical chemical properties, so from the composition we can estimate the chemistry of the interval, and it also has physical properties for every material type as well, so we can see the hardness of each material type. We can estimate the lump percentage, so I know the lump percentage is the percentage of the chips or the material that gets split into particles that are greater than 6.3 mils and less than 6.3 mils. So this is useful for different marketing purposes. The lump material might have different chemical attributes as well, for example. Each material type has a density value as well, so there's chemical properties which can be used for resource evaluation, and the physical properties are typically used for planning and marketing purposes. So we can estimate the composition not only of the interval, but also of a deposit once we have the logging data. So there's a number of problems with the logging. Firstly is just the volume of data to process. So Rio's a big company, they're drilling hundreds of kilometres of these RC holes every year, and they're logging every 2 metres of it. So it's a lot of manual interpretation of the chips that are coming out. The logging is subjective, so you're not only looking at they're looking at the colour of the chips, the hardness of the chips and so on, but some of these chips, once you get the really small things, they can be easily confused. So there's some errors with that. There's also some material that goes through the sieve, so as part of the logging they pull the chips up through a sieve, and the very, very friable material can be lost through the sieve. Estimating those percentages as well, on the previous slide that example was rounded to the nearest 10%, so obviously if you're rounding to the nearest 5 or 10%, you're going to get some errors introduced. Obviously there's significant financial implications if you get the grade wrong. If you think that you've got a lot of goethite but in fact it's shale, but they're all both soft and yellow, for example, then that's going to be a problem downstream. And there's also handling problems as well. So this is a particular type of goethite. This is an ochreous goethite. It gets confused with shale a fair bit, and this will come up again in the presentation. But this particular type of goethite, it's a bit nasty because it's very porous, and so when it's wet it gets very sticky and it has this tendency to go and clog the screens in a crusher. So as part of the logging and planning, you need to make sure that you blend the things in the right order so you don't block the crusher and then lead to downtime, which means that you don't make any money. So to mitigate these problems, there's a need to validate the logging. So the validation is a process in which we correct the logged composition that has been estimated at the rig, and we compare the theoretical chemistry values for that logged composition against the assays that come back from the second sample of that interval that went to the lab for assaying. So going through and correcting the logging for every 2 metre interval for these hundreds of kilometres is obviously pretty time consuming. The validation process itself, even though you're trying to get from what I've explained, it's numerically trying to get a correct solution. It can still be a subjective process because there's different material types that have been used. People that might have been trained on one site might be, they might prefer to use a particular material type compared to people that were trained on a different site. So this is a subjective process, yet it's still essential for accurate grade estimation. Just to summarise the process, we have the material type classification system in the top right. We log the RC chips in terms of those material types. The second sample goes down the left-hand side and that's sent off for assaying. And then we have this validation process here in which the material types that have been logged and their percentages are adjusted such that we match both the lab assays and the physical properties of that logged composition. So what I'm going to be talking about here is this validation step. So we've developed an auto-validation assistant. It's a process in which we semi-automate the validation process. It's not a complete replacement. It's also not a black box either, so the geologists can go through and see exactly what's been done to their logged composition during validation. So the material type classification scheme, it's got over 100 material types. You would think that given such a wide range of, say, chemical and physical attributes, there's got to be some combination of these types if you have so many possibilities, that you could quite easily find some percentage of a subset of these types to match the assays. But obviously there's a lot of constraints, so geologically it has to make sense. There's a number of end member types that, for example, if you had something that's high in silica and high in alumina, you don't want to choose, say, a high silica type and a high alumina type. It's more likely to be some sort of kaolinite type that's high in both of those elements. So we need to look at the geological context of the types. We want to maintain the physical properties of the logged compositions, such as the hardness and the lump percentage and so on that I was talking about before. And also, as well as matching the chemistry and making sure that we don't use the end member types just to satisfy the chemistry, some of these material types have physical and chemical values that are very similar, but they're used in different geological contexts. So some types, for example, the quartz and the chert here, which are predominantly silica, the quartz might be used in detritus only, and once you get to the bedded material, you might log chert. So this is used downstream in modelling, and it's a cue that people need to use later on in the process. Similarly for the shale and clay types. These are our two favourite types. It's actually come out looking very, very different on this screen. The ochreous goethite and the shale are the two commonly confused types that are very different chemically. Physically, the shale should look a bit more yellow than that. Made it look like it's quite an easy problem, but once you get the smaller RC chips, it's quite easy to confuse these two types. So that's a 5 centimetre chunk that's fairly big. So the auto-validation assistant that we developed, there's a few different steps. So firstly, we had to undertake a training process in which we looked at the logging, and we got a number of expert validators to go through and validate these logged intervals, and we recorded the process in which they performed geologically informed substitutions of material types, and we wanted to record the different scenarios, so geological and geochemical scenarios in which they applied these substitutions. We learnt the different contexts in which material types were used, and then we put all this training data into the auto-validation assistant, which processes these training rules and produces a number of validated compositions. And these are all presented to the user at the end. They're presented with the composition of material types and a confidence value for each composition as well. And the confidence value basically ranks the different compositions based on the chemical match to the lab assays and also the similarity to the physical properties and how well that combination of material types makes sense geologically, both with the set of material types in that combination and the stratigraphy in which the material was logged. The key aim was not to do this in a vacuum. It's not just a goal-seeking exercise where we want to optimise things numerically. We also wanted to respect the original logging that was performed on the rig and we wanted to embrace the geologist's knowledge. So once the geologist has logged the material, then they validate it, they can see the compositions themselves, and they might have some experience of what material is commonly underlogged or overlogged in an area. So we make sure that the geologist is kept in the loop. So to learn the different material type substitutions that were performed in validation, we presented, it was about a dozen validators with a large data set to validate. So we created a number of standards intervals. So these intervals were all mocked up. So we had theoretical chemistry from a composition that we created. And then we deliberately introduced known common logging errors. And we'll see some more about this shortly. But we also got the users to validate. In total, they validated 4,500 intervals. It wasn't getting someone to do 4,500 intervals each for an experiment for us, because that would be a bit torturous. But we captured a lot of results from these intervals, and we separated these rules into different sets of rules for detrital intervals, for mineralised bedded, and for shale intervals, because typically there's different sets of material types or different associations found in these classes of stratigraphy. In practice, a person who's sitting down and validating will take some time to have a look at what errors they're trying to correct. And after a lot of practice, because they're doing the same thing over and over, it's a very mechanical process, so the geologists don't really enjoy doing it. It's a bit of a, it's sort of punishment for logging it badly, I guess. But yeah, it's not something they look forward to doing each day, and they spend a lot of time each week having to validate their logging. So after a lot of time, they can get quite good at saying, okay, I have to correct this particular assay error. I'll change this material type, that material type, this material type, and add another material as well in order to get the right chemistry. But what we wanted them to do was validate step by step. So instead of them trying to jump from the logged straight to the validated composition, we wanted them to go through and step by step change 2 material types at a time. So if they increased, for example, a particular type of goethite and they reduced the percentage of shale, we wanted to see exactly what they were trying to do there. So we had to capture basically the threads connecting the 2 different material types that they were trying to exchange. And once we had that, there should be some sort of either similar chemistry or similar physical attributes that they were trying to maintain during validation. As part of this, they didn't necessarily take the most direct route to the validated solution, but we managed to record this data to maintain the physical characteristics of the composition. So we've got this pretty diagram. So this is basically summarising all of the material type that was swapped during training. I've thrown out a bunch of material types that were below a threshold. Down the right-hand side, we have the various material types that are shown around the border of this circle. So we can see the 3-letter codes. The thicknesses of each of these cords connecting 2 material types is proportional to the quantity of those types that were exchanged during the training process. It probably helps if I isolate one of the types. So this is our ochreous goethite. This is the porous, soft, yellow goethite that I was talking about before that blocks the screens. We can see that it's the length around the perimeter is quite big, so it's actually involved in a lot of validation. The 2 main swaps we can see here are made between GOL and shale, as shown with this one. So we know that physically these 2 types are quite similar, but we know that chemically we're trying to, if you swap your shale for GOL, you're trying to increase the iron grade but decrease the silica and alumina. What we can't see here is the direction in which the material was swapped, but as you'll see soon, we're looking for the relative quantities of each of the assay elements and just trying to visualise these exchanges. The other main swap here with GOL is this one down here to HGF. So HGF is a friable type, and it's a bit more hematitic than the GOL type. So this would have been made to increase the iron grade slightly while maintaining the friable physical attribute. just going, oh, still see it. There's another material type isolated here. So the shale, as we've seen, it's commonly swapped for GOL and commonly swapped for HGF as well. So these three are commonly interchanged with each other. The interesting thing was that when we created this, it was nice to be able to quantify these changes that were commonly being made. I think it was fairly well known that the same logging errors were being made over and over, and these exchanges were having to be made during manual validation a lot. But it wasn't until we actually showed this to some of the geologists that it's like, oh, okay, well that's great to confirm what we already thought. So that's summarising the amount of material that was exchanged between two different types. In order to actually apply the substitutions, we needed to look at the scenarios, the chemical scenarios in which they were exchanged. So this is the assay suite here, so it's a 10-element suite that was being recorded. And we looked at the assay error, so this is the difference between the lab assay and the theoretical chemistry that we estimated from the logged composition. So we took that error, and at each step, when someone made an exchange of material types, we created a normalised vector, so we got the difference in the assays, divided it by the maximum value, so we had a vector with the maximum value of 1, and then we associated this vector with a material type that was added and a material type that was removed at this point. And so we built up this large database of rules. We also rounded these. We can see that these are all multiples of 0.2. We rounded the elements and collated similar rules where we had similar assay error vectors and we were exchanging the same material types. So in our algorithm, we performed a big lookup where when we're trying to do the auto-validation, we look up the assay error that we're currently trying to correct. We find all of the rules within 45 degrees of the assay error that we're trying to correct. This sounds like it's going to create a lot of rules, but in fact, in practice, it's pretty quick because you can throw away a lot of rules that involve material types that you don't currently have in your logged composition. In the algorithm, we actually we associate each of these rules with a material type to add and a material type to remove. We only change the subset of material types that are selected in the composition. We don't directly exchange, say, 5% of this shale for 5% of quartz or something like that. We run an optimisation method to optimise for the actual percentage values. Just to step through this, there might be an interval that's logged at the rig as a set of 4 material types here. And so we take the logged composition, calculate the theoretical chemistry, compare that to the lab assay and get the error. Then we look up a set of rules. So one of the rules might be saying to remove material type C. So from that point, we apply that rule. And then we run the optimisation step and we get a new composition here. So we have 5% of material type A still, 25% of B and 70% of D. Another rule might be to completely remove material type C and add material type E. So we can see that alternative shown here. So these are all branches from that logged composition. The third rule might be saying to add material type E, and another rule might be saying add material type F. So at this point we have a number of different compositions, and we repeat this process because in practice you'll need to exchange various material types several times to get from the logged composition to the validated composition that satisfies the chemistry. To get the actual percentages of the material types, we run the optimisation method, as I said, and we're looking at various different attributes. So we're looking at the assays, obviously. So during manual validation, the geologists have to try and adjust the material type so that the theoretical composition is within some threshold or tolerance percentage of the assay value for every element. These tolerance values might be different. So, for example, for your iron, you might have say like 60% iron or something, so you can afford to have a larger error in the iron grade than, for example, for sulfur or for phos. So we perform the optimization in terms of what we've called an error tolerance factor. So this is just the percentage of that tolerance that's allowed. So if the iron tolerance is, say, 5%, then an error tolerance factor of 0.5 is going to be 2.5%. So that's one aspect of the optimization. We're also trying to minimise the change in the lump percentage, so maintaining the physical properties for the downstream prediction, and also minimising changes in the hardness. So this is one way in which we can respect the original logging that was performed at the rig. We used a library called AlgLib, which has a number of numerical algorithms in it, and there's a few other cheats as well. So just to cut off large spaces of the search space, for example, if your silica assay is, say, 10%, then you don't want any one material type to contribute more than 10% silica overall. So that's how we're exchanging the material types and getting the right percentages to satisfy the hardness and the assay constraints. Geologically, though, we still need to confirm that all of those compositions that we have make sense. So the way that we did this was we went through 60,000, roughly, intervals that had historically been logged and validated. So each of these intervals had been seen by a geologist twice, and we assumed that the combination of material types that was selected by the geologist was a sensible set of material types. So they hadn't just randomly picked materials that made sense chemically. Once again, we classified these rules into our three classes of detritus, mineralised bed and shale intervals. And what we wanted to look at with these constraints was to understand two things. So firstly, we wanted to find out what's a valid combination of material types. Have we seen, given a proposed validated composition, have we seen this particular combination before? If we haven't, is there some way in which we can go from a historically seen combination of material types to what's been proposed? So we used a set of algorithms called, they come under market basket analysis algorithms. You've probably all seen them before. It's basically where you go to, if you've used Amazon and you've bought, say, a collection of a basket of goods, then that's a combination of material types in this case. So you can basically go through a whole set of combinations of things and find the most popular ones. There's also the association rules, which is the second set. So association rules, if you have bought a particular item, then you might go to Amazon and it will say, oh, if you bought this, then you might also like this book as well. And so given every item, there'll be a score in which that item is linked to another item. So in terms of material types, we just said, like, if you've logged a particular, say, a hard goethite, then you're probably going to be logging a soft goethite as well. You might also be logging a hematite goethite hybrid that's also hard, but you might not have such a high score for logging, say, a gibbsite or something like that. So we can find clusters of related material types here. The other thing that we looked at with these historically logged and validated intervals was the frequencies in which each material type was logged with particular characteristics. So for every interval, as well as logging the material types, the colour of that interval, the chip shape of the interval and so on, all these other physical properties are logged. So we had a look at the frequencies in which each material type had particular physical characteristics in terms of colour and chip shape. And so given a validated composition that's been proposed by the algorithm, we can go back and see if that set of material types matches the logged physical properties as well. These are just some results of what we found from looking at the combinations of material types. The algorithm actually came up and we kept the top couple of thousand different combinations, but yeah, just for simplicity, all I'm showing here is the top ranked pairs and triplets of material types in each stratigraphic class. The actual descriptions are shown down here of each of the material types, but I'll talk through them. Firstly, going through the detritus types. we can see that the top ranked pair was the clay type and GOE, so that's an earthy medium hardness goethite. Second ranked pair was clay and GOL, which is the ochreous goethite, and we have GOV, which is a vitreous goethite, logged with clay, third most commonly in detritus. If we have a look at the shales, we can see that we get the same GOL type as over here, except instead of clay, we're logging shale. We get the same GOE type as shown in detritus here, but instead of being logged with clay, it's logged with shale in the shale intervals. So this is one way in which we're understanding the context in which different material types are used. Just looking at some of the other examples, typically overall we get a kaolinite type and a goethite or a hematite or a hematitic goethite type. So that's pretty much one of these other things that confirms a lot of things that you often see but was never quantified before in the data. So those rules, observing what was logged with what else, that's basically like a positive kind of thing, so that's where we can see something has actually been done. We also applied some penalties where there's specific rules where things don't occur, so we needed to penalise the algorithm for doing something that we haven't seen before. So one of the examples is where it's chosen a combination of material types that we haven't seen. There's some other rules as well, such as using a hydrated type when we're outside of the hydrated zone. Some material types might be chemically and physically, they might have the same properties, but one should only be used in the hydrated zone and one shouldn't. Other conflicting types, for example, using a clay and a shale together when they should be used for markers for different parts of the stratigraphy. And also some types, such as pisolites, they're pretty obvious when they're there, and they're obvious when they're not there, so chemically it might be a good fit to add, say, a pisolite type to one of your intervals. And we might have seen that before, but if it hasn't been logged in this particular interval, then it's probably not there. So you don't want to go introducing something that would be obvious to the logger. So this is just summarising the entire algorithm, and the thing to note here is that it's very similar to what's performed manually, except we've just automated it. So we take the logged composition, and then say if you're validating it manually, you'll swap material types, you'll adjust the percentages. We've added this intermediate step to look at the context in which different material types are used. And then we repeat the process. So we go back and we swap material types. So this is the same as what I was showing in that tree before. The number of iterations of this algorithm, we chose 5 steps. One of the things that we saw in the training data was that, I think it's 96% on there, 96% of intervals are validated with 5 or fewer steps. So it's nice to be able to, as part of the training data, we trained the algorithm, but we also managed to measure a lot of these things that were suspected but never actually confirmed quantitatively before. The final step is to display the validated compositions to the user, and they each have a confidence value, so the user can go through, and the final step is for them to choose an appropriate composition based on the logging, based on their intuition, and they're shown 10 different solutions, but we'll come to the actual rankings shortly. In terms of the algorithm, as you've seen, it's a collection of rules. It's fairly straightforward, and it basically mimics what everyone's doing manually. We deliberately chose this approach because we wanted to be able to go through and audit the different steps that were taken by the algorithm at each step. There's a couple of things. So we wanted to see what the algorithm was doing. We also wanted to be able to see if the algorithm kept making the same mistake over and over again, if it was adding the wrong type. We could go into the training rules and just say, hey, don't use this rule anymore. Or if there's some random geology that only occurs in one particular place that we hadn't seen in the training data, we wanted to be able to manually add some rules. Also, Rios they've been around for a while and have different logging schemes, so sometimes some of the old logging sneaks through, so we didn't want to be able to, didn't want the algorithm to add some old logging codes that aren't used anymore. That would just confuse everyone. So looking at the results, we evaluated a couple of different aspects of the algorithm. So firstly, this is back to front to the way I've presented it before, but this is looking at the geological context and set of material types. So we got some geologists to go through and apply the algorithm to 2,000 intervals basically, and we looked at the results that they chose. So they could choose from a list of 10 proposed solutions, and if they wanted to, they could go through and they could discard them completely and say, I want to add my own types, or they could adjust the percentages of the selected types. So if the algorithm had presented a composition that had, say, only 1% of a particular type, but it was logged as being, say, 5%, and they'd made a note saying that this was definitely present, so they might want to boost that percentage back to 5% for a type. So in almost 3/4 of cases, the geologist selected one of the validated compositions that the auto-validation assistant proposed, and they didn't change it. In a further 9% of cases, they accepted the geological combination of material types, so it means we've done a good job in selecting something that made sense geologically, but they'd adjusted the percentage based on, for example, the logging notes that I'd mentioned before. So in about 5/6 of cases, we got a good sensible set of material types. In terms of the answers that they chose out of the top 10, in 56% of the time, they chose the top-ranked solution, and on average, it was the 2.1th ranked solution. Don't know how you'd actually say that, but I'll go with that. But yeah, we were pretty happy with these results in terms of the geological set of material types that were chosen, and the numerical accuracy was also acceptable to the users. We performed some more validation to evaluate the accuracy in terms of the assays. So we validated the entire deposit. This deposit was used on a different area to the training data that we got the people to validate initially. So there might have been some slightly different geology. The results here are shown in terms of the assay error tolerance factor, which I've mentioned before. So a tolerance of 1 for an element means that we're right on the limit of what we allow the variation to be for that element. But it's important to note that any composition that has all of the error tolerances within 1 is equally valid. So you don't want to over-optimise. I think that's on the next slide, actually. So we don't want to over-optimise just to get this error tolerance down to 0, because we're trying to optimise for other factors as well, such as the hardness and maintaining the right colour and so on. We've got this chart. Basically, the chart's divided up into, we've got 4 blocks here. So we're looking at the iron error, the error in silica, alumina, and for the LOI. Each of these, we've got the detritus intervals, the mineralised bedded, looking at the shale intervals, and then we've grouped them all together. So just looking at the mineralised intervals, well, the first thing to see is that these blue lines are all fairly big. So the blue lines are the errors from the logged compositions. These are the ones we're trying to correct, so it's nice to see that the validated compositions are better numerically than the logged ones, because that's the whole aim of the thing. But what we can see here is that the manual validations, so for example here, is generally pretty good. The auto-validated compositions are slightly better in some cases, but remember that anything less than 1 is equally good. In terms of so the top chart is for the mineralised intervals. The bottom chart also includes so the low-grade intervals, so where the iron's less than, say, 55%. Typically, if you're manually validating these intervals, you won't pay as much attention to it, because if you can see that it's low grade, it's probably not going to be sent off to the plant and so on. So manually they will pay less attention to these. So that's one reason why the manual validation error is slightly larger for example, down here than it is for the mineralised intervals. But numerically, we can see that the auto validator is still getting good results. Now, one of the things that was that came up over and over again when people are manually logging and manually validating is that the change between shale and the ochreous goethite. So we looked at the percentages of these types in the different compositions. What we can see here is that typically we've got the same colour scheme here, so we've got the logged value first, then the manually validated one, and then the auto-validated composition. So these are just the mean values for the intervals. We can see that typically the kaolinite types, so your shale and your clays, are overlogged, and on average they're reduced quite a lot during validation. And conversely, the ochreous goethites, so these are the ones that look quite similar, they're typically underlogged. So this is one of the reasons why the validation is so important, and why we wanted to try and be a bit more consistent with how we're performing validation. So we can see that so generally your goethites are underlogged and your kaolinites are overlogged. Just to combine all of that into one chart, we can see here we've got the kaolinites being decreased in percentage during validation, and on average the goethites are increased. We also looked at the hardness of the various compositions as well. So the hardness is just looked at in terms of hard, medium and friable types. The change in hardness is the percentage of material that was changed from, say, a hard bin to the medium bin, or from the medium bin to the friable bin. Generally it's fairly consistent, especially for the mineralised intervals. Once again, the all columns here include the waste intervals, and so less attention is generally paid to those during manual validation, which could explain why this value, for example, is a bit higher than the auto-validated value. But otherwise we're getting fairly similar results, which we're really happy with. So in summary, we looked at, we performed a training step to understand the common material type substitutions through supervised validation, and we looked at the common combinations of material types that were logged historically, and we developed the algorithm to apply these material type substitution rules and ensure that we had valid combinations of material types. Performing the validation using the auto-validation assistant is faster than doing it manually, and we're getting good accuracy with it, while we're keeping the geologists in the loop while they have to choose a validated composition. We're getting geologically sensible results. The solutions that we're producing are accepted by the users, and Rio is currently deploying this on a number of sites. And we'd like to thank all the geologists at Rio who have helped us by validating those 4,000 intervals for us.
Thank you. Did they give you any sense of the cost benefit that this was providing, or is that...
We have a rough idea, but yeah, it's confidential. So, but it's reducing so it's reducing the labour by, say, over half.
Okay. Sweet. Any other questions?
And the frustration as well.
Yeah, there you go.
All the intervals are 1 metre?
Oh, 2 metres.
So, did you have a feel for how much that 2 metre composite was maybe, obviously put across the boundary? Yeah, absolutely. So we were using, say, like those 3 classes, and even within, say, the not only just crossing the boundaries, but within, say, the mineralised bedded stuff, there's some narrow shale bands as well, so it might only be, say, 20, 30 centimetres thick. But yeah, that's going to be a lot of shale coming out in that 2 metre interval. With the rules, we divided them into the 3 classes, but you preferentially chose rules from the same stratigraphic class. But if you got in a pickle and you couldn't apply any of those, you could, say, if you're in the bedded stuff, in the mineralised bedded stuff, you can pull out some of the shale rules, for example. But yeah, there's a bonus for using the rules from the same class that you're in.
Have they tried automated XRD as an alternative way?
Yeah, I don't know. We're looking at just the just looking at the current process and trying to do that. So even with XRD, I'm not. So with the XRD, you get the assays, but you still need to log, for example, the other physical properties. So looking at the hardness and that kind of stuff for your downstream prediction. So yeah, there'd probably still be some sort of need for logging, I'd imagine.